Our next video is going to be about exponential growth, which is a really specific kind of Diff EQ. So when you see an exponential growth Diff EQ, you're either usually going to be handed an equation or you're going to be handed a statement that is intimidating because people hate word problems. But let's talk first about the statement. So when you hear the statement, the rate of change, so the rate of change of blank, I'm going to leave it as blank, is proportional to blank, that's called exponential growth or exponential decay in theory, but they're the same concept. It's just whether the values are getting bigger or smaller. So sometimes it's the rate of change of a population is proportional to the population. Sometimes it's the rate of change of puppies is proportional to the puppies. I don't know. It doesn't really matter what it is. So when you hear this phrase, right, the rate of change of a population is proportional to the population, what they're describing is essentially dy dt, right, the rate of change of y with respect to t, right, so how y is changing over how time is changing, right, is proportional to y, right? So dy dt equals ky. This is the Diff EQ that describes exponential growth. So when you hear this phrase, it translates to this. We see this so often that it's worth us just memorizing what it solves to so that we have that in our brains, but I'm going to walk you through what it is anyway. So if we were to separate this differential equation, we're going to leave the k on this side. So I'm going to divide the y over, and I'm going to leave the k over here with this dt. When I do the antiderivative of both sides, right, my left-hand side is going to have an antiderivative that is the natural log of the absolute value of y. And we'll deal with that absolute value in a minute. On my right-hand side, I'm going to get a k times t, right, because k is some coefficient, and I up the power of the non-existent t to 1, plus some arbitrary constant c. So when I solve this for y, I'm going to do that by exponentiating. So that means I'm going to raise both sides in their entirety, right, whole thing, to the e. So this e to the natural log is going to cancel, and it's just going to give me y. Now, I understand you're probably thinking, why isn't that an absolute value of y? And you're right, in theory, there's an absolute value there and we'll deal with it. But I'm going to cover that up in a really easy way in just a second. So e to the kt times e to the c, right? Because that's what happens when we add numbers in an exponent. It means that they are individually the powers on the basis. And I'm going to recall this as c sub 1. I'm going to rename it and say this is some other c. Because this new c has the property that it is some arbitrary constant and could be positive or negative, right, positive or negative, that takes care of why I'm not concerned that I got rid of that absolute value of y. So if the initial condition I'm given somehow gives me a y that's negative, this plus or minus option in my c sub 1, the idea that c sub 1 could be either sign, is going to take care of that. So what I end up getting is that this thing is always, every single time, forever, going to integrate to y equals c e to the kt. Now I just renamed it c sub 1, but I'm going to call it c here for convenience. Sometimes you'll see this written as y equals y naught e to the kt, where y naught is an initial starting value, right? So this is an initial condition or starting value. And it makes sense because if you were to plug in t is 0 here, you would get e to the 0 regardless of what k is, and that's a 1. So if you were to plug in a time of 0, you'd just get whatever this y naught is out. So it's ideally what you want to get from this is that this phrase, right, this phrase, which says the rate of change of blank is proportional to blank, translates to this differential equation, dy dt equals ky. It may not be y, it could be p for population or something else, and that will always integrate to y equals c e to the kt or y naught e to the kt. Cool.